recording, I'm going to show you how to determine several things about an electrochemical cell, or in other words, a battery. So batteries are spontaneous redox reactions, and we can calculate the voltage given a standard reduction potential sheet. So to start with, I'm going to draw the cell just by making kind of a beaker. I'm going to draw two lines for a salt bridge. And the salt bridge, in this case, if we read the last bullet, contains some K plus and some Cl minus. It asked me to draw the cell labeling the anode and the cathode, so I know that the two electrodes are going to be aluminum and zinc. So the first thing I need to figure out is who the anode and who the cathode is going to be. But before I do that, let's go ahead and label the solutions. And so it tells me that the aluminum is sitting in some aluminum plus 3, and the zinc is sitting in some zinc plus 2 solution. And normally those are going to be, it says an acidic solution, but most of the time they're going to be nitrate solutions. And so I know that they're going to have some type of negative, maybe a nitrate or a chloride or something like that, floating around in solution with them. So to determine which one of these guys is oxidized and which is reduced, I need the reduction potential sheet. So we're going to just scooch over to that and take a look and find the aluminum and the zinc. So I'm going to scroll down a little bit and see if I can find these. And so here's my aluminum. I'm looking for a plus 3 and a neutral. And same thing for the zinc. And so zinc is going to be a little higher. Here it is. So zinc plus 2, and then also. So those kind of match up to my electrodes and my solutions. The trouble is both of them cannot be reduced. If you notice, the electrons are both being gained for both the zinc and the aluminum. So one of them is going to have to turn. So what I do is I look at the potential and I figure out who is the most positive, and that guy is going to be able to stay, and the one that's the most negative is going to turn into an oxidation. So I compare the two numbers, a negative 0.76 and a negative 1.66. And so since a negative 1.66 is more negative, that's going to switch over and become written as an oxidation. So I'm going to switch the reaction to aluminum, aluminum plus 3 electrons, and that's going to change the sign of the potential to a positive 1.66, because if you flip the reaction, you flip the sign. So what this means is the negative 0.76 is how much voltage it's going to take for that zinc to gain those electrons, and it would take 1.66, so I'd have to hook this up to a battery to make that happen. So now I have my knowing which one's oxidized and which is reduced. So I'm going to go back to my cell. So know that aluminum is going to be oxidized, and so this is oxidation, so that's my anode. And so therefore zinc is being reduced, and that's my cathode, because red cat and anox. So then it asked me to write the half reactions. Well, we kind of have those over there on that reduction potential, but it's pretty simple that the thing that's going to be oxidized is going to start off in its pure form normally, and then it's going to become more positive because it's going to lose electrons, where the zinc is going to start off as it's more positive, and it's going to become less positive by gaining electrons. And so those are my half reactions for the two cells. So now it wants me to balance this overall reaction, and so since I have aluminum, becoming aluminum plus 3 electrons, and I have zinc with 2 electrons, becoming zinc, elemental zinc, what I'm going to do is I need to balance my electrons first. So I know I need to multiply this reaction by 2. And this reaction by 3. So when I do that, I get 2 aluminums, 2 aluminum ions, plus 6 electrons. and then I get 6 electrons plus 3 zinc ions plus 3 zinc atoms. So then all I'm going to do is cancel my electrons and then combine terms, or combine the reactants and the products. So I have 2 aluminum, 3 zinc ions, yield 2 aluminum ions, plus 3 zinc atoms. And that's my overall balanced equation. So then the next thing it wants to do, and we've already labeled oxidation reduction, so we're good there. So the next thing is we want to write the line notation for the cell. And so the line notation is very simple. It's kind of like a diagram of the battery, that you start with what's oxidized. So I know I'm going to start with aluminum, and I just write that down. And I draw a line to the next thing it does. So no, this is going to be wearing away and forming aluminum ions, and so I go aluminum plus 3. Then I draw 2 lines to represent the salt bridge. So I go across the salt bridge, and the first thing I hit is some zinc, and then draw a line, and that zinc is actually going to coat. So my zinc is going to increase. So I'm going to become zinc metal. So that's my line notation. So I've just done that. Now to calculate the standard electrical potential, remember, and I'm going to kind of clean up my page here a little bit, remember that when we worked these out, we looked at this potential for each one of these guys on the reduction potential. So we found that the aluminum potential was a negative 1.66 written as a reduction, but we changed it to a positive 1.66 when we wrote it as an oxidation, where the zinc was a negative 0.76 for its voltage. So what we do is we just take our voltages, our oxidized and our reduced, and we add them up. Or you could say reduced minus oxidized and not flip the sign. So if I add that together, I end up with 0.9 volts. And so that would be the potential if I have 1 molar solutions of each one. So now I have my electrical potential. But then it says, what would happen to the voltage if the concentration of aluminum is reduced to 0.5? So if I go back to that balanced equation that we had down here, so if I reduce this to 0.5 molar, leaving my standard for the zinc. So the deal is that reactions will actually shift to replace whatever you remove, or if you add extra, to use it up. It's called Le Chatelier's principle. Kind of like when you take an egg from a chicken. If you take the egg, it'll lay another one. So I've removed some aluminum, so the reaction will shift to create more of that aluminum ion. And anytime you go towards product, you increase your voltage. So for this question, I would have a higher voltage than the 0.9 volts because of that shift. So then in our drawing we can see it says which electrode will be increasing in mass and which will be losing in mass. So I know, just kind of even based on that line notation, that the zinc is growing. It's forming more elemental zinc. So that's why I have kind of this drawn. So this is growing. But then the aluminum is reducing down and becoming aluminum plus 3. So aluminum will lose mass. So the anode goes down in mass, so loss of mass, where the cathode is going to gain mass because you're forming the element on there. And so then the last question is about the salt bridge. Well, I know that as I'm forming more aluminum plus 3, that this side is becoming more positive. And as the zinc is being reduced, this side is becoming more negative. So I need a way to balance that out. Well, that's what the salt bridge helps me do. So the negative part of the salt bridge will travel over and help balance out that positive. And actually some of this positive in the form of the K and the form of the aluminum plus 3 will go this way. So this is going to gain K plus, where this over on this side will gain the Cl minus, just to keep that charge balanced out. So pretty much that's how we go through and work through a electrochemical question.